So you are welcome again for today's session. So we want to quickly rerun the example we did yesterday before we proceed, so that we'll go over it so that we can grasp it better. If you remember, the example we looked at yesterday was this example on the treatment regimen that resulted into atrial ventricular tachycardia, which is called suicide de Pontis. So this is an example of log linear analysis. A Poisson regression, which the outcome or the exposure variable are categorical, referred to it as log linear analysis. Actually, Poisson is log linear. Even what's the name? Logistic regression is a form of log linear because you took logarithm of the odds. So, but they don't usually call it like that. But they call even the whole Poisson regression. We don't call it log linear. Just the aspect where all the exposure variables are categorical. So you can represent it in the contingency table. Look at this. The example now we are able to represent in the contingency table. This is a form of logistic Poisson regression that is called log linear analysis. I think we have explained all those things and how we use AND to generate the beta. The way we want to look at is just to rerun it. So let me share the data set. So this is data that I think everybody can see. And do something now. Analyze. Go to generalized linear model. Under it, generalized linear model also. So under somebody
generalize.
Sorry, the dream just went out. I'm back now. So we take Poisson, then log instead of identity. Hello, can you hear me? So somebody is talking. Okay. Now, yesterday I talked about the generalized linear model being made up of 3 components. The response random component, which is the response variable, this is the outcome, and the systematic component, which is the exposure, and the future variables, and the link function, which link the two. Now, the link function, when you are talking of whatever is normally distributed, those ones that were originally general linear model, like a linear regression, ANOVA, and COVA, they are systematic, the the response, the component usually normally distributed, that is continuous variable. And that is what we see normal here. By default, you see normal. But for Poisson, it's Poisson because it's log, is Poisson distribution. And the link function for Poisson is log. So those are the things that still come to play here. So the theoretical basis we discussed yesterday, you have to put it in. Now, when you do that, you now go to the next. The next button will be response. The response variable is the presence of, to say, the pointage. You move it as dependent variable. Then when you do that, you move to the next one, which is predictor. Predictor is the treatment. Don't mind me, in my own Sunday, I put another treatment here, but this is the treatment. The treatment, move it in. Now, if the exposure variable is categorical, you move it as factor. If it is continuous, you move it as covariate. Can you see that? There's a difference. So any exposure variable that is categorical, you move it under factors. If it is a continuous variable, you move it as covariate. Here now is categorical because the treatment is either regimen 1 or regimen 2. So it's categorical. You now go to model. The model you see will give you by default main effect. You move that in as model. Then if you don't move it, if you remember yesterday, just like what we did in logistic regression, when you want to first of all run the model, we may first of all run the model without, we may not run the model without the exposure. We just look at how it will be. That is, without the exposure variable, that is the baseline.
What would be the value of y?
Yes.
The intercept.
Yes, the intercept without the, intercept is usually the value of y when x is equal to 0. So when x is not there, y can still have value. So that before you put in the x, you may want to see the way it goes. So in that case, you not feed in this model. Under model now, you go to estimation. Well, you can either use model-based or as a robust-based or model-based estimator, any of them. So it just changes, what it changes there is either you use this or this, is the computation of the standard error. That is the only difference. And then every other thing does not change. You may leave it, you may say robust estimator or model-based estimator. Now, statistic. Luckily, this one is on check, include exponential parameter estimate. That is, if you don't include it, it will not show you the exponential. That is where when you are taking the log, because you cannot interpret the log, because you are using y, you are calculating log y, so that you don't model it. So when you log y does not make anything, because at the end of the day, what it will give you is that is the log of the exponential, is the log. Beta will be the log, change in the log of y, by only change in s. Is it the log of y you are going to say? So for you to now change it back to the real scale, normal scale from logarithm, you now do anti-logarithm, which is exponential. So he's saying that you want to have it. Of course, you want to have it. You want to have the exponential. If you don't click it, it will not give it to you. So after you have done that, so somebody, please, everybody should mute if you are not talking. Okay. So after you have done that, if you look at it, I didn't feed in the model. So I say, okay, now. It will now alert me, no effect has been specified. Therefore, an intercept only model will be fit. Do you want to fit an intercept only model? If I say no now, it want me to go and put it. If I say yes, it will run it. That's what I just said. That yes, has run it. Let me show the output. Somebody shouted. So, but you can hear me now, okay? Let me show the output. Look at the output now. I think everybody can see the output. You see, let me just go directly, because some of those paraphernalia, they are just some of those things we did in logistic regression. Now, look at the final table here. You will see that only the intercept. It doesn't show any x, only the intercept. So, and what is showing us that intercept itself is given on its own. That is the model. That is the null now. So when we do the next one now, I want to see if there's any improvement on the model. And as I've said before, when if you are dealing with, if let's say it's normal, if you remember, when we do linear regression, we said that.
Hello? Excuse
yes.
me.
You cannot hear me?
Yes, sir. You said like it is significant, but I just saw the confidence interval.
You saw the confidence interval. Okay, let me, because somebody was talking confidence interval. And look at it now. The confidence interval does not look at it now. Okay, I know what it does. It cross is 0?
Yes.
Hello,
does it cross 1 rather? Does it cross 1? Yes.
Hello, sir.
Yes, sir.
I want to change my laptop. It's giving me a problem. So you may see, if you may see a new laptop or something, I want to off this one and change it.
No problem, no problem. Go on.
Okay, but sorry, because I was seeing 2 confidence intervals. I saw the first one, then I'm not.
No, you are okay. You are looking at the standard error. If you want to look at the exponential, that's what you do. Even this other one also does not cross 0, and this one does not. It shows even the standard error for this one. You look at it, that one also. So is this? It doesn't cross 0, and this one does not cross 1.
Okay, yeah, right. Okay,
cross 1. So now let's go and fit the model. We have not fit the model now. If we remember yesterday, this is what we first of all calculated with Anne. When we say, okay, 30 out of 50, then 52. 30 out of 52 people, 30 have to say the Pontes. And if you 30 divided 52, it gives you it gives you 0.577, and if you calculate the logarithm is minus 0.550. Yes, I mean, so that's just it. So let's now rerun it to now include the model. So analyze, generalized linear, then generalized linear. It just to every other thing is already fit, just for me to go and put the treatment as the model. That's all. And just say okay, because every other thing I've clicked them. So if you scroll down, can you see the result? Can you see now it has included the treatment? But there's something I did there. If you look at it, there's something. Okay, let me go back. I want to show you something. If you are going to analyze generalized linear model, under the predictor, when you put in the treatment and now come to options, that was what I was searching for it, what really happened. So if you look at the way we coded it, how do you want to, because here, you want to, okay, which one are you going to use as, even if you didn't even put 0 and 1, you know, the computer, they have made, if you didn't even create the dummy 0 and 1, if you just remember the computer, they have a way of creating the dummy. The computer has a way, they program. So do you want to do ascending or descending? Ascending means that if you say it's ascending, if you click ascending, you are trying to say that the one you have coded number 1 will be the, you know, you start from, because you start from the smallest, is the last one you are making the reference. I don't know if you understand now. And the way we coded this one, we coded is 0 and 1. We coded the regimen 2 0 and the regimen 1 1. And we want to make regimen 1 that we coded 1 as the reference. So we now say ascending. If you say ascending now, it will make the last or the highest one to be the reference. You get it now? The highest one to be the reference, the highest coding. But if you say descending, it will make the lower coding to be reference. If you say use the data order, of course, what it will do for you, it will use ascending, because the data order is from 0 to this. So let's use ascending, because the way we have coded it, we want to make number 1 the reference as opposed to the 0. So if you do that, look at the result. Look at it. So look at the way it is now. Okay, treatment number 1 is the reference. That's why I put it 0 here. Why this one, the treatment 2 is 0, which is the treatment regimen 2. So if you look at it now, if you look at the estimate here is 1.6. So what he's telling you is that for everybody that is regimen 2, as opposed to regimen 1, is going to be about how many percent if you change this 60% more, like the increase in the chance of having to say is 60% increase. So how do you say? Look at 1.6060. Okay, there's something I want to I still want to discuss about interpreting this thing, because interpretation, because of it was already late yesterday. How do you interpret the result? So here now, if you shift the decimal, okay, if you remember yesterday, I said that if your beta is 0, it means that log, if your beta is 0, then the anti-log will be 1. You know, the logarithm of 1 is 0. So if the beta is 0, the anti-log, yeah, the exponential will be 1. But if the beta is greater than 1, greater than 0, like in this case now, is 0.47, 0 point something is greater than 0, the anti-log, what you have will be greater than 1. That's why you have 1.6. If the beta is less than 0, that is where you are seeing minus, what you have is minus, the anti-log here will be less than 1. If you look at the intercept now, the beta here is less than 1, and that's where the anti-log here is less than, the beta is less than 0, the anti-log is less than 1. So now the interpretation is that when the anti-log is greater than 1, that is the exponential is greater than 1, it means that there's an increased chance of having that attribute, like of having to say now, the chance for everybody that receive treatment regimen 2 instead of treatment regimen 1, the chance increase is multiplied times 60%. That's 60% increase. How do you know? If you multiply, you remove 1, remove 100%, you remove 1 from this. 1 from 1.6 is will be 0.6, and express that percentage, that's 60%. So that, see if it, okay, look at the one I did before. When I made I use ascending, the first one I ran before I remember, because look at it. In the same data, it give us, look at it, in the same 0.47, that is the beta, but it's negative, minus. It means that the chance will be, the anti-log exponential will be greater than 1, in less than 1 rather. So when it is less than 1 now, if you remove this 1 from this one, it will give you negative. If you express this by percentage, it's telling you by how much the thing will reduce. So if you, the chance of having to say it will reduce. What he's saying is that what you put here is treatment 1. That is if somebody is making noise, please mute yourself if you want to discuss in your place. So instead of if somebody received treatment 1, regimen 1 instead of regimen 2, that should that the chance of having to this to say as will reduce. That is why the exponent is less than 1. I don't know if you understand. I don't know if there any question, because people were saying that we were too fast yesterday. So,
Hello, sir.
yes, sir.
Good evening, sir.
Good evening.
Yes, sir. I want to ask that, can we say that that reduction is about 38 to 40% reduction?
Is it? No, it's not. Actually, it should not be that. It should be still the same. Should be around 60. Well, the reduction.
No,
Yes,
the
yes,
increase should be
yes. It's true.
60%.
Yes, if you remove, yeah, you are right. If you remove 1, yes, it is just, yes, you remove 1 from this one, minus 30 to 0.3 something.
Yes.
Yes, you are
It will
right.
be like 30% reduction.
Something reduction.
Thank
Yes,
you, sir.
yes. Welcome.
Thank you, sir.
Welcome. So, any other one? Okay, is it clear now, Dr. Ikobo? Is it clear?
It's clear, it's clear.
Okay. So, any other? So, I can go to this. Just for us to continue where we stopped yesterday. Yes. Now, this is the result of what we just discussed. So let's look at second example. From the second example also, we throw light to a lot of things. It will open a lot of discussion. If you remember, the example we did yesterday, we will just explain now. It's something you can use even logistic regression to run. We even ran it with logistic regression yesterday. But we found out that the Poisson is still more powerful than the logistic, because we put it on contingency table. Because if you look at it, both the outcome and the exposure is yes or no. Is it there or not there? The example. And that is the example they usually call log linear, because you use a contingency. But this second example is not a contingency. Even you see table, it's not all the table that is a contingency table. You know, contingency table has to do with table that arrange frequency in matrix. When you involving more than one variable, when you oh, sorry, doctor, say that it has been blocked. No, I'm not. It's Dr. Ikobo was trying to, Dr. Abasi, trying to connect, but he said that it's like it's blocked. It's not blocked. How can I block it?
I don't have any problem with not me.
No, it's not you,
me.
Dr. Abasi, it's Dr. Isaac.
It's not me.
Yeah. He says since it has been blocked because he initially got it, but now that's error code 503. Which error code? I don't think. How do we do that now? Just 1 minute. Let me stop. Let me pause the recording so that. Yes, what I was discussing. So yesterday example, which we just concluded now, is you can put it on contingency table, but this one, when you are not dealing with rates as per the number, it's not whether it happened or not now. The number. Example we have now is looking at the number of awards. Number of awards some students receive in the university as the outcome variable. Now when you say number, someone can receive no award, 0. Can be 1, can be 2, can be 3. So it's not whether somebody receive award or not now. Number of award. And that's a very good candidate for Poisson regression, number of something. So in this case now, you cannot use contingency table to show it. And in addition to that difference now, this example also has two more than one exposure variable. Then the program the person is running, is the general program or academic program or vocational program, is a factor. Then the score in the mass score is a factor. So we have to, if you look at the data is award. But I want us to see, but I only show the aspect that we saw with hand here is the award as the outcome variable and the program the person is running as the exposure variable. Then the other exposure variable, which is a score in mathematics, is in the data set because that one is quantitative. Can you see now? So we are having three variables involved now. The first variable, which is the outcome variable, is a discrete variable from 0 to infinity. That is a number of awards. It's quantitative, it's not categorical, but it's not continuous. It's a count variable. That's the outcome. The first exposure now is the program the person is running, which is categorical, and there are three categories. It's either general or academic or vocational program. Now, the other one, the third one, which is another exposure, another exposure is the score in the mathematics. That one is a continuous variable. Now, number one, you cannot show this one on contingency table because the outcome is count. That's why. Now, we cannot show the relationship between it and the mass on a table also, unless you group the mass into a collapse. It's just like the way you cannot show age, just put all the age on the table, unless you range it. But because we have an exposure variable which has three categories, so we know what we now did is to show the mean. You know, you can calculate the mean count in number of awards now for each of the category, and that is what you just have there. And that is, if you want to do this type of analysis, that's the first forum, just like what we did yesterday. We did a cross tabulation to first of all have a view, to see the direction before you know how to do your analysis. Just like the way when you do chi-square, you will have done some initial bivariate analysis before you decide how you're going to run your regression, either linear or logistic or whatever. It's the same thing with this Poisson regression. You will have done some analysis, and the result of the analysis will then determine the direction you're going to take in running the Poisson regression. Now, I want somebody to share award. The name of the data set is award. So I don't know if somebody can share so that we'll still come back to come and see what we have on the slide. But for us to see what I just to calculate the mean based on the three categories of the program. What I show on this table is not that it's not part of the question. It's initial analysis that bring it out just to summarize up. Who is sharing? If there's nobody, maybe I share my own, but I would like to when somebody participate. Dr. Adeshino, you are not using your computer? Hello?
I'm using my computer, sir.
You want to share now?
But my SPSS is old.
You're not serious. So when with all these things that I send version 25 to people. Didn't I send?
I've not seen it, sir.
No,
I'm using version 20.
20. It's okay.
Okay, I don't know, sir.
Okay, run it. No, your question is not hold. Run it with version 20. Share with version 20.
Okay, award.
Yes.
Yes, award. Okay, you can permit me to share, sir.
Yes, I have. Dr. Hello, welcome. Professor Yemi, welcome.
Thank you, sir.
Yes, sir.
Sorry, I'm using two devices.
Yes, I can see. I can see.
My this is not stable.
No problem.
Yeah, Dr. Kulu, thank you.
There is identity. I can see the two. Is where people use.
Can you see my screen?
Yeah, we can see. Yes.
Okay.
So that's great. Okay, before we run, I want us to see, because some people were talking of coding, all those stuff, dummy. If we look at it now, the ID is just the serial number, just to identify the person as number one, number two. That one does not go into the analysis. Then the three variables are number underscore award, that's the number of award, and the person received. It can be 0 if the person did not receive award, or 1 or 2 or 3, as many as possible. That's the dependent variable. Then the program the person is running, there are 3 categories here: vocational, academic, and general. Then we have the mathematics score, math score. Yeah, we're trying to see maybe people that are good at mathematics are more likely to award. That's what this one is just saying. Now, it's good. Go to view. Click on that between edit and data. Click on
data.
No, view. Beside the, click on it.
I've clicked on it, sir.
Uncheck the value label. Uncheck it. Click on that thing. Uncheck it. The value label. So immediately, can you see now? This program was labeled before. It has changed to 1, 2. So if you want to see, go to variable view. You see the way we label what we label what. Because it was the label that was showing, but we essentially enter a 1 to 3. Click on the yes, where you have value of a program. Let's see. Yeah. Can you see 1 is general, 2 is academic, 3 is vocational. Now, if you want to use, because there are 3 categories and it's categorical. Normally, you're supposed to do what we call dummy variable. Then why so that you don't do is that the computer has made provision to dummy by itself. No, they have programmed it. But it's still good for you to, because especially if you are running linear regression now, sometimes you may have to. So that one also make provision, but this one is more, well, if you are running logistic regression, sometimes you may want to create the dummy yourself. Sometimes you may want to use what they did there and the way they arrange it. So it's good to see the way we create the dummy. Go back to the data view. Okay, thank you. So here now, if you want to create dummy, it's very simple. You want to, if we know we have 1 to 3, general 1, academic 2, vocational 3. But before we create, dummy, let's follow, because there is the what you go to use, which one you go to use as a reference may be determined or conditioned by what you see. Yes, that one makes sense. So before we talk about creating dummy now, let's first of all explore the data. The exploration I want us to do is to do the mean value of the outcome. If you remember when we talk about Poisson distribution, when we say the probability of having a particular value, so is the E, which is the natural constant raised to power minus lambda. Lambda is the parameter, is the mean rate, which you want to estimate the mean rate. So lambda E over raised to power minus lambda, then lambda raised to power x over s factorial. We show it yesterday, it's in our slide. Now, what I just want to say here is that the The mean, the parameter estimate here is the mean rate now. It's not proportion. Yesterday, if you remember the one we did yesterday, we still talk much about it. It's proportion because it's either yes or no. It's either the to say it, no to say it. So you can say what percentage so to say it. But here it's not like that because here is not whether you receive award or not. It's the number of award. So it can be 0, 1, 2, 3, like that. So the best way to summarize it, rather than summarize it with proportional, is to summarize with the mean average value. So let's go to analyze. Analyze. Want to
Analyze, I'm there, sir.
Yes, go to compare means. Compare means. Okay. Then click on which are over. But click on means there. Means under the compare means. No, it's an over you are compare means the mean number 1. Yes. Yeah, this is slow. Yes. Okay, move the dependent list is the number of award. The dependent list, number of award. Then you want to, the independent list is type of program. You want to know the mean award by the different type of program. That's all. Click OK. So you have to stop sharing this one and share the output with us. Stop sharing this one and share the output. Stop sharing this one first. If you don't stop sharing, you will not see the output. It will be
okay.
And if you don't stop sharing, it will be confusing you. Yes. Stop sharing, then go back to share. You will see the output. You now double click on it. Go back to share screen. Okay, that's great.
Are you seeing the output?
We can see it here. We can see it. So you
Okay.
see, there are 200 of them, 200 students, and the mean out of the 200 students, there are 45 under the general program, 105 under the 105 under the academic, and 50 under the vocation, make it 200. You will see the mean. The mean of the general is 0.2. The mean number of award is 0.2. The mean number of award for academic is 1. The mean number of award for vocational is 0.24. So in this case now, you may say, okay, what you want to do, you see the standard deviation is there also, but there are some other issue I don't want to discuss that. You can just leave for another time, because you expect the mean and the standard deviation not to be too far, because one of the assumptions of Poisson regression is that the mean and the variance, yes, they are not too, yes, they are not too far. Now, you will see from here now you can decide, okay, which one, we know that it is lowest with general, highest with academic. Now, and we have coded them 1 to 3. So which one you can decide to which one you're going to use if you these 3 groups now, which one do you want to use as the reference?
General.
You can use general, you can use vocation, but let's use vocation. Let's just use vocation. So in that case, if vocation is number 3, we want to use, let's use vocation as our reference. It doesn't really matter if we use general also, it's just like the interpretation to be the same thing, but what you are comparing to what differ. So let's use vocation. Now, you can stop sharing. Yes, because that was what I wanted to achieve by asking you to share. So if you look at it, it's the same thing I put here. The only thing we didn't show in that one is that If you don't, you just do the mean without cross-tabulating into the category. The overall mean is 0.363. That's what I put here. If you run the mean also without saying you are separating it into 3 groups, the overall mean is 0.3. With the standard deviation, you can see. Now, if you are to apply the formula, if you remember the formula, the logarithm of y is going to be beta 0 plus beta 1 x1 s1 and beta 2 s2. You know we have 2 variables now. This one is a multiple now. We have 2 variables bx x1 and x2. Now, this multiple, the variable I'm talking of here, the multiple I'm talking of here, I'm not talking of the mathematics, so I've not even brought the mathematics score here. In as much that you have 3 categories of this factor now, you have 2 dummy. You're going to compare general with vocational and academic with vocational. So it has given you 2 dummy, 2 variables there. If it is only 2 categories, then it will be 1 dummy. You are comparing one with the other one. It will just be like 1 variable, just like what we did yesterday. But in this case, even with the categorical that has 3 categories, there are is created B1, X1, and S2 to read. And if we now add mathematics to it, that would be B3X3. But now we just want to, for case when we want to run it, we are going to run mathematics also with the bet. For case of for illustration, let's first of all use the category. Now, just as usual, when y without x, what we did yesterday, now you will see something here. Yesterday, when we were looking at this other one, which is contingency, to say it on, because it's contingency table, what we look at is that we look at the logarithm of the proportion. What proportion has to say over the total, that is the number that have to say over the total proportion. But here, the outcome here is not summarized as proportion. It's summarized as mean. So what you look at is the logarithm of the mean. So if you want to first of all look at, let's look at generally now without x. Is the mean, general mean, without this, without dividing them into groups, the overall mean of the award, number of awards is 0.363. So logarithm of 0.63 is equal to B0, which is the intercept, plus B10, B, you know, here now without S, so both X1 and S2 will be 0. So it will give you this. This is the intercept when Y is not, X is not there. Just like what is it? Before you can, if you want to predict anything and without any exposure, is the mean. If it's a quantitative variable, it's the mean you use to predict. Oh, what is the average? What is the average? That's the best summary, the only summary you can give. What is the average? If it is something is categorical, you say, what is the proportion that have this attribute? So just like what we did yesterday. So here now, it has given us. So if you now come program vocation now, we want to start with we want to use vocation as the reference. Program vocation as the reference. What is the mean vocation? Is 0.24. So logarithm of 0.24 is B0 plus BX in B1 times 0, B2 times 0. You know, both of them in this case also, because reference, vocation is reference. So these two domains, they are for general and academics. So instead, you are looking at the reference alone. So the value of the general and academic, see X and S, S1 and S0. So when you do that, so with the presence of X now, the presence of the program, the intercept is the beta for the intercept. The intercept is this, minus 1.42712. Now, when you come to program as general, in that case, the mean for general is 0.2 is equal to B0, beta 0 plus beta 1 times 1. You know, you are now holding this one as 1. You are holding the other one as 0 because this is like creating, that's still the dummy we are talking of now. Because that's beta x1, the dummy is for the general. So it's only the general that will be 1. Then vocation, academic will be 0. So at the end of the day, 0 times this will be 0, it will be out. Okay, hope you can hear me. If you can hear me, let me know.
Yeah.
Yes,
I
yes,
can
we
hear you,
can.
sir.
Okay, because the thing was, because when I was trying to mute Prof, what was making noise in said, so the thing was telling me as if I was muted. Okay, now if you now do this for general now, it will now give you, of course, it's only this one is 0, so it's going to be the antilog of 0.2 will be minus 1.60944 is for both B0, beta 0 plus beta 1. So we already know beta, we already know beta 0. So if you substitute for the value of the beta 0 here, so if you now take it to this side, this minus will become plus here. So if you solve it, it will give you this. So beta 1 will be minus 0.18232. Then for beta 2 now, if you go to academic, program academic, the mean is 1. Logarithm of 1, B0, they know beta 1 will be times 0 is coded 0, while beta 2 is 1 for academic. So it's the same thing. So it's going to be 0 is equal to B0 plus B2. So I will already know B0, beta 0. You bring it here, so the answer would be beta 2 will be plus. Can you see the beta 0 here, intercept is minus 1.427, but this one will be plus, because when you change over, it will be plus 1.42712. If you try to calculate their antilog, this is what it will give you. Number 1, the antilogarithm of this, the odd for intercept. We are talking of the intercept without, sorry, it's not the reference intercept, this first one. You know, it still remain what it is. Yeah, then, okay, that's for the, okay, I think that one is for the, sorry, it's for the reference. Then the antilog, you know, that one is the reference. The odds for the general versus vocational. Sorry, actually, it's a misnomer here. It's where I copy. It's not odd ratio per se, because if we don't talk about odd ratio here, I will remove it. It's just the exponential, just exponential. We just call it exponential. It's not,
Thank
no,
you, sir.
it's
I
not,
was getting confused.
yes, it's not odd ratio. It's exponential. So when you copy something from the other slide I used, I forgot to. So it's exponential. It's not odd per se. It's not odd ratio. It's the exponential. Exponential. Because the interpretation is different. It's not now. vocation divided by general versus vocation. So you know we have already, that is beta 1, which we calculated here. If you calculate the antilog of beta 1, it gives you 0.83. This is the percentage. If you remember, you know, Dr. Adedotun was saying that we should have, let's use, if we have used general, because general has the lowest. If you use general compare, we expect the odd to be greater than 1. You know, because every other thing you are comparing with that 0.2 should be greater. So we know that because vocation is more than general. So when you choose general instead of vocational, it will be less than 1. So what it's telling you is that those people that are in general, they are less likely to get a work than vocation. That's what it's telling you. So for general, no, sorry, keep on.
Sorry.
Sorry.
You know, academics.
Yeah, that's what I just saw. Academic.
Academic versus vocation.
Academic, yes. Academic versus vocational. Is this? It will give you 4 points. So if somebody is in academic instead of vocational, how many times his chance increase by, you know, how many percentage? More than 400 and 300 and something. Because if you remove 1 from this one, it's going to be 3.1, 316, 17% increase. You know, the chance is higher with academic to get award than vocational. That is what. So look at it. So it's not odd ratio, it's just the how many times is more, because it's a multiplication effect. It's not how many times more than, it's just the multiplication, it's not odd ratio. So though they call it rate ratio, it's not odd ratio, rate ratio. Though the interpretation is almost the same.
Yes, sir.
Yes.
Can you interpret just make the general versus vocational statement, just interpret it.
Vocation, general, and the vocation is less likely to, the vocation, no, the general is less likely to get award. So if somebody is in general instead of vocation, there's a reduction, because if you remove this one from this one, it gives you minus maybe 17%. So 17% less likely to have, the person is 17% less likely to have, to get award than if it's in vocation. That's person in general. Yes. Whereas the person in academics is 317 times, more likely to have award more than vocation.
So why did you see the 317 times?
Remove, okay, remove 1 from 4.1617. It gives you 3.17. Express it as percentage. That's 300.
No, you said I should remove 1.
4, look at the rate ratio here, 4.17, right?
Yes.
Minus 1. That's minus 1. Okay, you can say it's the same 4.17 mean 470%. You know that one?
Yes.
Remove 100% from it.
Oh,
70%.
Okay.
So it's try to say when something increased by 300%, when something is 200%, you say it has increased by 100%, it has doubled, right? If something is 200%, that shows that it has doubled.
Yes, sir. Yes, sir.
So that's what it means. So let's now run it. Then we now include the mathematics also. Why we cannot, you may ask me, why can't we demonstrate the way we have demonstrated the relationship between the outcome and the program? Why can't we do it mathematics code? You cannot do it today. You can do it, it's long. That's why computer is there. You have to do for each value, you know, this one is already categorized, but that one is not categorized. And if you go and categorize, you have defeated it. You are changed to categorize variable. So that's why you have to calculate this beta for each value of the mass score. So, but the program, computer knows how to do it within seconds. No matter how many they are, it will do and give us the result. So this one that is manageable to manage, we just use it to demonstrate. It's the same logic. I don't know if you get what I'm saying now. It's just like now, if you want to press your computer now, when we say mean, compare me where we now put program. If we put mathematics score, you know what you give you? If we do that in mean for all the values of the mathematics down 200, maybe 200 or whatever, it will just run it for you. So it doesn't make to manage it will be a problem. So that is why it's not feasible, or it doesn't even make sense to be doing that with hand. But thank God for programming, the computer will do it for you. So let's share again. Dr. Additional, share now. Let's run it. Let's run it. Are you there? Dr. Additional?
Yes, I'm here, sir.
Okay, share.
Okay. I should share a word.
Share. And share
Yes.
what you did yesterday now. What you did yesterday, what you just did now, share the same thing. The output.
Doctor, we're going to share, you know.
Okay, no problem.
Okay,
Yeah,
I'm sharing now.
anybody can share. Anybody that's ready.
I'm sharing now. I'm sharing now.
Okay, we can see. Yes. So now, I want us to see, now we have already made up our mind now that, okay, we are using reference, vocation as reference. In that case, we want to create dummy for the other two. So how do you create dummy for the other two? If you want to, but we are not going to use it. Let's create it. It's the same thing. Let's create it.
We go to data.
I will use it. Yes, go to data. So Dr. Ernest, be looking. Select cases. You go to data, select cases. Now, if condition is satisfied, click if. And move that type of program. No, type of program. That's what we want to create dummy for. Program. Move it. Is equal to 1. You know, we want to create first dummy for general. 1. Continue. Because we have coded general as 1. Continue. Yes. If you look at it, can everybody see the variable view now in data view? You will see that it has created a filter, and that filter, anything that is not general, that is their program that is not 1 here, it has marked it. Why did you log out?
I want to go and open that.
No, don't open it. What are you opening? It's there. We are seeing it now.
Okay.
We are seeing it.
Okay.
It's showing. No. It's not the result now. What you did is not. It's only the programming that comes to the result. It's variable data editor window, data view. Go to that data view. Share that data view, not this one. Stop sharing.
Okay, sir.
I'm just explaining something. Because sometimes if you assume that people understand it, because by the time people will not know, okay, yes, if they want to do non-discover, how do you create it on me? Now, if you look at it, what you did, look at there's a variable that is filter with $, something like that. So what he has done, if you scroll down now, you see all the ones that are programmed, that are 1 under the program that are general, it marked them 1. The one that any other one, He marked them 0. And he canceled them, and if you look at it, he canceled them. So all you need to do, you have created dummy for this one, and you have created dummy for general. So go to variable view, click on variable. So change that filter to general. I call it general dummy. No spacing. Okay, dummy. That's great. So you can remove, cancel this thing out. This program is called to filter. Remove it, just delete. So leave that one. Okay, you want to say yes or no? Okay, yeah. Click on. No. Just click on one of them. It's already there. Just click on one of them. Change it to yes. That's selected. Change to yes. It doesn't change anything, but it just the labeling. So instead of say selected, not selected, change. Then click on the other one. Click on the other one. Click on the other one. I change it to no, not selected. Just delete all to T. That's all. It's okay. Change. So you have created. Click OK. You have created dummy for general. You now go to again data. Go back to that data. Select. Click. You click on this. Where do you go back? If. See, click on that if now. Click on it. Change down 1 to 2.
Are we not going to reset first?
Eh?
Are we not going to reset? I wanted to reset first.
It's the same program now. It's the same variable you are creating.
Okay.
So you change it to 2.
Okay, sir.
Dash 2 is the academics. Continue. So go to variable view. So it has marked all the academic 1. The remaining is 0. Go to variable view. No, variable view. So you change it to academic dummy. Remove this one. So you don't need to click on that, the first one you did. Yes or no, the general domain. You don't need to bother yourself. Cancel this one. Just click on the first one. Click on that one. Right click. Close it. Close. Yes. Just OK. Click OK. Right click now. Just right click the way it is. It's highlighted now. Right click. Copy. Yeah. Paste it here. Right click here and paste. That one, yes, no, the same thing. You have pasted it. So now go back to the data. If you look at it, before you go back, go to data view. You see that it has all those things cancelled still there. So go back to data and remove that thing. Otherwise, all those ones you cancel, it will not include them in any analysis you do. Go to data. That's in all cases. Okay. So we have created, we have created 2 dummies now. For 3, the variable is 3 category, we created 2 dummies. Dr. Enes, is it clear? You see the way we create dummy now? Dr.
Yes,
Wale?
yes.
Okay.
I follow it.
Yeah, that's good. Okay, let's go and do the analysis. Yes. Go to analyze now. Generalized linear model, not this one. Generalized linear model. Yeah, generalized linear model. Then go to custom. Because we are dealing with categorical. No, not actually. The outcome is count. Use Poisson linear. Wait, remove that custom. Come here. You know, the other type, it is recommended if the outcome category is contingency, you use the custom. But if the outcome category is count, you use Poisson. Click on Poisson log linear. So I don't know. Okay, go to response. So we want to start. Don't forget about that. Click on, okay, you know what we want to do. Click on general, dummy, and academic. No, so click on number of award as your number of award as the dependent. Move it. Yes, move to predictor. The next one, predictor. Move the two dummy you created. Move them to factor. Let's see. Now, move to model. Move both of them inside. You know, if you want to, first of all, I just neglected one. If you want to, you don't want to show, you want to first of all show where there's no X, it will show also, but everybody knows that one. Now move to estimation. Just leave it as, you know, you can change to robust or any of them. It doesn't actually, you can change it to robust or leave it as model-based estimator. Go to statistics. Click on include exponential parameter estimate down here. Otherwise, it will not give you the estimate. Yes. Click OK. To share the results. Share the results. Yeah. Now scroll down. Scroll down completely. Yes, I think it's that is scatter some things here. Okay. If you look at the only thing I just wanted to look at, no, you know, because of those the way it arranged here. Now go back to analyze. Go back to analyze. Yes, continue now. Generalize my model. Just go to only the predictor. Go to only the predictor. Predictor. Then remove, return all those, the two of them, return, and just return them, and put the program, put only the program. No mathematics, put only the program. And option, click on option. Now as you put the, click no, because you are going to click. You have click on this thing. I say you should click on option here. Option. Now, you want to, can you see now? You leave it as ascending because that's the way it creates its own dummy for us. Help us arrange it. We want, if you say ascending, it will use the last as the reference. And the last 1, 2, 3 is our vocation, which we use as our reference. So it's okay like that. Can you see? If let's say we'll come back and rerun it later, you know, you were suggesting that why can't we use general, number one.
General, yes.
And if you say descending, it will use the general as the something, as the reference. But let's leave it as ascending. This is where to change, you know. So you don't actually need to create the dummy. Creating a dummy now, the way it works here is not like a logistic regression. If you were to be logistic regression now, the dummy is very straightforward. If you create it, there's a space for you to choose this one. So, but this one, everything you create is using, because by default, this ascending, you already put it there. So it will be using everything there. That's why it's scattered the result with dummy. So that's why when you are running, you don't need to create that dummy for it. So it will automatically, when you say ascending now, it will use the last one as your reference. Click continue. Click on the model. Then move the program in. If you remember, immediately, since you have removed all those, you remove them from the model. Whatever you choose, that you move it in. Move it in now. Click OK. You see. So scroll down completely. Yes. So you will see. You see the result now. You see this table is saying here. Let me look at annotation. Look at it. Program 3, you now see is 0. A set to 0 because it is parameter in a redundancy. Can you see? So you use program is equal to 3, which is the vocation, as the reference. So we now did for program 1 and program 2. Can you see? Program 1 is general. Program number 2 is academic. And you remember all the things we calculated the other time when we say the logarithm of 0.2. Well, after we have done it, we have calculated beta 1. Our beta 1 was minus 0.1823 something. Then our beta 2 was 1.427. Our intercept was minus 1.427, if you remember. So if you look at their exponential, of course, the intercept will be the same thing as the reference. If you know the value of the reference, the mean of the reference was 0.24, the mean of vocation. And whereas there be the beta, the difference between the vocation and the academic is 0.38. We know that the vocation is higher, the award is more, they have more award than the general. And that's why, if you remember, when we calculated the antilog of that beta 1, it was 0.83. So it's telling us that the general are less likely to receive award. So the number of awards reduced, by 17% compared with vocation. Whereas if you look at program 2, which is the academics, you see 4 points. This is telling you that compared with vocation, if somebody is academic, to be 317 times receive award. The number of award will be 317 times times that of vocation. That is the interpretation. And if you look at their confidence interval, you want to know if it's significant or not, but you will see something that the program is not significant.
Please, sir, can you be using your pointer? Because I'm not even, when you were mentioning 300 or something, I was looking for like, but if you're using your pointer,
where is your mind? Is it not what we have solved before? That was why I was just, is it not what you had, the question you had before we have solved? Look at, the pointer is not right now. Wait. Okay. Let's color. Look at what I was saying. Look at it. If you remove 1 from 4 point, or if you express this one as percentage, it will be 470%. Remove 100% from 370%. That's what I said. So if you look at it, it's significant. Look at for program, it's not significant. Look at the p-value and look at the cross-check with the confidence interval. For the program, the confidence interval, you look at it. Are you seeing?
Yes, sir.
So you see 0 point something to 1 point something. So because if the confidence, if it is just 100%, that is 1. It means that it is the same. So that is why it must not cross 1. This one has crossed 1, but this one is not cross 1. Any question? So the interpretation is just a little bit different. There is almost the same thing with logistic regression. There is no odd ratio here. And the logic why it is not odd ratio is that if you remember, for logistic regression, the logarithm you calculated is a logarithm of odd, logarithm of p over 1 minus p. You examine that. And so the beta will now be change in the log odd per unit change in X. But here, the beta here is change in log per unit change in log Y per unit change in X. Can you see? If it is linear regression, change in Y the way it is per unit change in X. The unit of Y is the unit of Y. If it's linear regression, change in Y per unit change in X. The logistic change in log odd per unit change in X. Why this one change in log Y per unit change in X? So for logistic regression now, it's going to be, you know, when we say something change per unit change, it meaning that that beta is over 1 when you say per unit change. So when you now change it to odd ratio, what is telling you, it's log odd you did. So it's comparing change in odd of one group per unit change in odd of the other group. So it's comparing the odd of one group with the odd of the other group. That is why they call it odd ratio, ratio of 2 odds. But this one is rate. What you are mentioning actually is rate. The average there is rate. It's rate ratio. It's not odd ratio. This one is rate ratio. So change in log of the rate. Can you see? Per unit change in head. So in this one now, is telling you when you now do the anti-log, you now begin like the rate. What is the change in rate per unit change rate of the other group you are comparing with? Like this one now, you are comparing the academic to vocation. So if there is a change, what is telling by how many times this one is more than change in the vocation, the rate of vocation. So it's more than it by 316 times multiplication. So it's just almost the same, but the trick. So it's not odd ratio, it's rate ratio. Any question? Any clarification? So it's very clear. Okay.
It's not very clear. It's not very clear. Huh?
Okay, how many people
can you hear me?
It's not clear, sir.
I can hear you.
Can you hear me?
One person.
I am not clear with how you got the 300.
Your this is not clear. I can't hear you. Your voice. Maybe you can send chat. Please, if your this is not, you don't.
Oh, can you hear me?
Yes, I can hear you now.
You can hear me?
Yes. But somebody is making noise.
Well, can you hear me?
I can hear you now.
Can you hear me?
There's somebody making noise in
You know,
background.
I'm not clear with nobody's making noise in my place. So.
I'm not saying it's you.
I'm not clear with how you got. I'm not clear with how you got the 300. Though you explained it when we were doing the mathematics, but
300.
It's not very clear to me.
Okay, don't worry.
Yes, is it?
Don't worry, I will. Okay, okay. Okay, I think I understand now. Yes, I can. Yes, I'm hearing you. I'm hearing you. Stop sharing, Dr. Adedoku.
Okay. Yeah.
Stop sharing. Yes, sir.
I think you tried to explain it yesterday.
Don't worry, I will explain it again. I'm going somewhere now. Okay, you want to explain? Okay, explain. You want to explain it, right? I want to show you something now. So, can you see this slide?
Yes, we are seeing it.
Yes, this is interpretation of the coefficient. So, if x1 is a continuous variable, that is, if the exposure variable is a continuous variable, then the quantity exponential beta minus 1 times 100 is either way, either you say, you know, the exponential come in decimal, it doesn't come in percentage. One also just mean if the exponential is 1, what does it mean? It means that this thing has not changed. Yes, I mean now. It doesn't by 1 unit increase in the exposure, the rate of the event has not changed. It's still 1. It's still 100% the way it is. If the rate was 20, it's still 20. That is, it's still 100% the way it is. It has not reduced, it has not increased. If it jack down, it has reduced by a certain percentage. If it jack up, it has increased by a certain percentage. So if something is 1, it means 100%. But if that thing is 1.6, what does it mean? 1.6, that one, if you want to now know what has, if 1 is still the same thing, but if it is 1.6, for you to know what has changed, the percentage change, you remove 1 from 1.6, it gives you 0.6. 0.6. And if you want to express it, just like the way we express our proportion, if you want to express 0.6 in percentage, that would be 60% increase. So if the thing is S1 is continuous variable, the quantity exponential minus 1 time expressed in percentage represent the estimated percentage change in mean response when S1 is increased by 1 unit and the other S variable are fixed. If X1 is a categorical variable like this case now, with several levels, then exponential b minus 1 expressed as 100% in percentage represent the estimated percentage ratio in mean response for the X1 is equal to 1. And that for the reference level provided the other X variable are unchanged. Now, what we are saying is that if that particular thing is 100%, it has not changed. Because what is it just means is that because you are actually comparing the academics and the vocation. So what is 1? It just means that look at this rate for this thing is the same thing with the vocation. But if it is now 4.16, which is what you see, it means that Yes, you can express it as 400 as 16%, or first of all remove that one. So what has he increased? What improvement increase has he made more than the vocation? It means that it has improved by 4.16 minus 1. That is 460 minus 100, making 316% ratio. So he's telling you that 316 times that what it will have been where if it were to be vocation. Simple. So though if you look at it down, it's because if you look at it, I have created two scenarios here. There's one for continuum, there's one for categorical. One we are dealing with now is categorical. We are going to run the mathematics. Though it's virtually the same thing, but the way we interpret the continuous one will be what we interpret for it. And whereas for the categorical, which we are dealing with now. So it's like comparing 400 and 300. If we are comparing 400 and 300, and 100 rather. If you are comparing 400 and 100, it's not division. So it's not actually odd ratio. It's not division. You are trying to compare. If we cannot say that it's 400 times. No, it's not 400 times. Because one here is 100%. Okay, somebody, I don't know if it's clearer now. Why not interpret it as 400? Why remove one? I think I've explained in that the question somebody prof asked. Is it clear now?
Yes, sir. Thank you very much, sir.
Yeah.
Yes,
okay.
sir.
Any other one? Okay, I want us to. Yes, sir. Go on.
Okay, what I was saying that what the difference between using general linear model and the generalized linear model that we're using to run this?
What is the difference? I think we explained that yesterday. Let me go to the slide. Let me go to the slide. I explained it yesterday. That even that was the we're trying to give. Yes. We first what started with, okay, what is general linear model? It refers to the conventional linear regression model for a continuous response variable given continuous or categorical predictor. Forget about the predictor. Somebody, speaker is echoing my voice. Please, everybody should off. Now, one make the one that are captured under general linear model, their outcome variable are continuous. That's all. Linear regression, ANOVA, and COVA. The reason is very simple. Since the outcome is on continuous scale, you can put the predictor on a continuous scale, on a linear scale, and see that for any increase, unit increase in this one, it will correspond to a particular increase or decrease in the outcome. But there are some outcomes that are not like that. Something that is yes or no, something that is categorical, or something that is rate like this. That the rate now does not is skewed. Because when you say rate of an event, you will discover that they call something zero inflated rate in Poisson regression. Because when you say number of, look at even the data set we are using, number of awards, you see majority 0,000. You didn't get any award. No, imagine you just sample award. Is it award for everybody like that? Is the university you gotta we want to know how many people receive award. Of course, a lot of people will not receive award. Is how many awards did you receive? It's going to be 0,000,000. It's only you now see some people that receive one there, and the more the number of awards, the less the number that even increase. So you go to that receive, you go to see that okay, the people that receive 0 award are the highest, followed by the people that receive 1. There's people that receive 2. So it's going to be rare for somebody to receive 5. So that type of distribution is skewed. So, and anything that is categorical also is skewed. In that case, if you put them, you cannot predict them. We explain it extensively when we're talking about logistic regression. Okay, maybe there's something. Let me share I'll still come back to this one. Let me share the slide for logistic regression and quickly explain. Because this one, you need to understand it. If you don't understand it, every other thing will just be like as if it's Greek. It's not clear. We explained something with that logistic regression slide because we went into town to the reason for using log transformation. These things. 1 minute. Okay, just 1 minute. I'll bring it out. Logistic. Yes. Yes, we discussed something, and I don't know if you can see this slide now. Are we together? Can you see the slide?
Yes, sir.
Yes, we have something like this. Though even the slide I show also, we have something like that. So one thing with linear is that the outcome variable you are trying to show, it has wide possibility. It can even have 0 value. That is why even in the graph, you know, if you look at it now, there's intercept here. It means that the graph can cross and even go to negative side. It can have negative values, so it has a wide range of value. So if there's any change anywhere in the exposure, so it gives room for the outcome to change very well. But in the situation where it is yes or no, no matter the change, whatever change, variation in any exposure, something that is yes or no, is either yes or no. I don't know if you get it now. So it's bounded. So and the yes or no now is now put on the probability scale, which is from 0 to 100 or 0 to 1. So it's bounded. Anything on probability scale, you know, probability is from 0 to 1. It cannot be less than 0. That shows that it cannot be negative. It cannot be greater than 1. It cannot be more than 100%. So it's bounded. And whenever something is yes or no, which we are using in logistics, the problem you now have is that even between the 1, 0, and 1, it can be anything between the better. Whenever the 0.5 will be something, anything 0.5 and above, we approximate it as 1, yes. And if the probability is less than 0.5, is no. So even though it's even bounded, but it dichotomizes it. Look at, that's why you see all the dotted point. It's either at 1 or at 0. No matter what effort you take in changing anything, you change. Just like you put in, you are trying to for somebody to improve. You invest. There's no change because the thing is not elastic. It can't change. So that is one thing with this type of thing. For you to now do that, so people not okay, intelligent people, they now came, you know what to do. The intelligent people, look at it, you remember. Can you see the, I'm showing this picture, I show this picture. So the intelligent people now,
Yes.
you know that for the thing, the one that follow normal distribution, the one that is continuous for linear model, all those one the outcome that is continuous, they follow normal distribution, normal situation. But now that we are dealing with proportion that is bounded between 0 and 1, that's 0 and 100. So though some people say that okay, if you take sample, something that followed by normal distribution, proportion, if you say sample many times, the sampling distribution also will follow normal distribution. That's what you are seeing here. The sampling distribution will follow, and it peak at 0.5. So most of that is why we say that if you throw a die, draw a coin, 0.5, 0.5, half, half, you know. Now, but the issue there is that it's still bounded. The intelligent people now, they know the relationship between proportion, which is the probability, risk, and odd. You know, we say that the proportion, the risk, the probability is between 0 and 1. But the odd is between 0 and infinity. Can you see? I think we demonstrated that. I think it's in one of the slides, which look at this. Can you see? When probability is 0, the odd, you know, the odd is probability over 1 minus probability. The odd is 0. When probability is halfway, 0.5, the odd has traveled double 1. You know, if probability is 0.5, it means that odd will be 0.5 over 1 minus 0.5. That will be 0.5 over 0.5, which will be 1. So when probability has a journey to travel from 0 to 1, if it has traveled halfway, the odd has doubled its own journey. When probability now complete journey from 0.5 to 1, the odd has gone to space, has gone to infinity. Can you see? Yes, sir. So if you try to plot a graph of odd on one side and probability on one side, if you look at the horizontal probability now from 0, the scale from 0 to 1, you can see. Whereas for the odd, because look at it, as the odd as it's coming out, at probability 0.5, the odd is just 1, just above 0 here. Can you see? The scale for probability is from 1, but this one is from 0 to infinity. This 50 is just for convenience because there's no, it's just no end. So that is why from that half now, when probability travel to reach 1, that graph would never touch 1. The odd is going to infinity. It's skewed. Do you get the vision? So the intelligent people now say, what do we do? Now, what they now do was that if you now plot, look at the odd now. If you plot it, that is why it's skewed. It does not follow normal distribution. But for probability, it will still follow normal. If you have, if you take sample many times, it will still follow normal distribution, but it's bounded. But the odd that is not so bounded, because at least it has leverage, it has 0 to infinity, but it doesn't have negative aspect. So the intelligent people, they now say, okay, no, since we have not gotten what we have, let's now do logarithm of odd. You know, when you now do logarithm of odd, you now answer the question. Because if you remember, logarithm of 1 is 0. Logarithm of anything less than 1 is negative. That is anything 0 point something, the logarithm is negative. Anything, logarithm of anything 1 point something, anything greater than 1 is positive. So we have already known that when the probability travel halfway, which is 0.5, odd has traveled 1. So that is the middle journey for probability. When you transform odd to log odd, it makes that 1. Can you see? 0, which is logarithm of 1, is 0, which corresponds with probability 0.5. You see now? So is the peak of the graph. To the other side, it will be negative to infinity. To the other side, it will be positive to infinity. So when you now do log odd, it's not normally distributed and is not bounded. Can you see now? So it's normally distributed, it's not bounded. Because the probability can be normally distributed if you have some repeated sample, but it's bounded. The odd that is a little bit stretched is skewed, but log odd is not bounded, is not skewed. Do you get the picture now? So when you now calculate log odd, When you now use it as a regression, it now behaves like a linear regression, because if you make any change anywhere in your, it accommodates the change in the outcome, because the outcome is log odd. Do you get the picture now? Because it's not only the same thing with, the Poisson. In the Poisson regression, instead of log, because this one is rate now, so instead of log odd, we just say logarithm of that rate. When you do the logarithm of rate also, it achieves the same thing for you what log odd did for logistic regression. So because we need to do some transformation for them to be able to behave as if it's linear, that is why we call it generalized. So for them to enter, to be accommodated, you need a link function. Those link functions is either the log odd, which log odd is called logit. Logarithm of odd is called logit. Then logarithm of just logarithm. That's what we use in Poisson. The log odd for logistic regression. I don't know if it's clear now. Is it clear?
Yes.
So I think it's clearer for everybody also. Something. Please, if you are not talking, off your, because it's reflecting my voice. Okay. Yeah. So if you look at what I just explained here now, I even explain it here in one of the, at least there's one of the graph that look at it also. Though it's just they didn't explain it much better. Look at the graph for linear regression. This is how normally this one is. This is how this one is. But for them to behave linearly, you need to transform. They are natural, the way they are naturally. For them to be, we have to change. So that change. Look at the first equation now. Event. Just this is the general linear model, but all of them also, they are under generalized, just like an extension. When you extend it, it accommodates. Even those that are general linear model, you see classify them as generalized linear model. So we now talk about the link function. Can you see now? So that's why in the generalized linear model now, you have three parts: random component, which is the outcome variable, the systematic component, which is the exposure variable, and the link function that link the outcome and the exposure, which we have here. For all those ones that were originally general linear model, which are linear regression, ANOVA, and COMBA, their link function is identity. There's no identity, just mean that you just identify them. There's no special, there's nothing, there's no transformation, it's just identity. Okay, this is your name. No transformation. That's meaning of that identity. But those ones that require transformation are the ones that were not general linear model, that is under the generalized, that they are accommodated. Logistic regression, the random variable is binomial for that's for binary logistic, and the link function is logit, which is logarithm of odd. While for log linear and Poisson is the same thing. What we did yesterday is the log linear. What we are doing today is Poisson. But both of them, they are log linear, because this log linear is well, anyone that the outcome variable, all of the exposure variable are categorical, and you can use contingency table. They call it log linear. For Poisson, it's still Poisson, but it's a form of log linear. But if anything outside that, you call it Poisson, but it's the same thing. So the example we did yesterday, we qualify as log linear, is still Poisson. It's log transformation also. Poisson, the one we are doing today, is log transformation. So I think Dr. Ikobo was asking one question. What was the question he was asking? I don't know if I've addressed it in all this long talk. Dr. Ikobo, is he there?
Yeah, my own was addressed before this one. I wasn't the one that asked this one. No.
Okay, this one is clear. Okay, your own has been addressed.
It's not from me.
Okay. I know that you are not the one. But I just want, okay, it's clear now. So where are we? I want Dr. Adedo, please share I want us to go and use, we want to reanalyze, we want to use the general as the reference. Let's use the general as the reference. Dr. Adeshina, is it there? Is it there? Maybe it's not there. Maybe I should do it. Maybe he has left the place. Okay, let me share my own. Okay. Award. Okay. Yes. Let's rerun the thing now. Generalized linear model. Generalized linear model is variable. Anyone even can actually use this response variable. Yes. Okay. So look at it. The program also, but I want to come now, instead of using ascending, let me use descending. To use descending now, it's going to make the number one we coded, which is the general program, as the reference. So I think that's all. I think other thing, I've put them. Yeah. Let me share the output. Can we see? Can somebody see?
Yes, sir.
You will see that now it has arranged it from type of program 3 down. Can you see? 3 is vocational, 2 is still academic, and the reference is 1, which is general. So because we know that the mean rate of our award is least with general. So when you are now comparing, because it has created 2 dummy, one for the vocational, one for the academics. So when you now compare it with the general, of course, the risk rate ratio will be greater than 1. That's what you are seeing. I don't know if you can see it. Can we see? Please, I want you to respond.
Yes, sir.
You can see that the interpretation will change now. Interpretation will change. Look at this one now. 1.44. So 44% increase, 45% increase. That is of the difference between vocational is better than general.
So why is it 45? Because it's 1 point. Okay, minus 1. Sorry, I guess.
Why the other one is 196% increase? Can we see?
Yes, sir.
Yes.
So
2.956.
Okay, sorry, I've even run everything. No, I've run mathematics with it. No, I want.
Yes.
Sorry, let me rerun it. Maybe it's because I'm coming back to run mathematics with it. Let me rerun it. I didn't know that I put mathematics because we are coming back to that mathematics. So under the okay, I didn't know that a math score was there. Yeah. Yes. So, it just went up. Let me be sure that. Sorry, it just went up. Yes, what I was showing. You know, I was wondering before. You know that when we use vocational, as the reference. It was 404 point something for academic. When we now use general as reference, academic is supposed to be bigger than 400 in 4 point something. So it's because we have removed the mathematics was there. If you look at it's 5. So I don't know if you get what I'm saying now. And if you look at the reference is 0.2 because that is the intercept. That will be the intercept because you are making the general, which the mean rate for general is 0.2. That would be the baseline, the intercept to compare other with. While the other one is 1.2, this one is 5. Is it clear? Let's go on. Maybe we should even leave it like this. Leave it like let's now include, let's now run mathematics separately before we now do magic together. Let's run the mathematics. Analyze, generalize linear model. Somebody's Dr. Additional, do you know, Dr. Yemi, mute yourself. It's echoing what I'm doing. So now let's remove the predictor. Let's run only mathematics. And I've said before, if the predictor is quantitative, is continuum, is covariate, you don't put it under factor. It's covariate. So you don't, the option does, because when you put factor that it has option. Option for which one is you're going to use as reference. But this one is the value straight. You now go to the model, you put it, the mathematics. And run it. So can we see the result? Can you see the result now? The race ratio is 1.09. So every time per unit increase in the score of mathematics, it is multiplied by 1.09. The rate will be multiplied by 1.09 for every unit. If you multiply by 1.09, you multiply by 1.09, and it's significant.
That's the rate of getting an award, sir.
Yes, sir. So that shows that if as somebody must anybody that if somebody maybe scores 60 and that person scores 61 in mathematics, the person that scores 61 is 1.09 times. It will have 1.09 times award than the other person that scores 60. That is, as the mark increased by 1 unit, then the rate of award increased by 1.09.
9%.
That is 9%. Thank you. So let's try to, like all these things, and there may be confounder. So let's now run them together, the two variables at the same time. So if you look at it, there are some similarity when you are running, like as if you are running regression, linear or logistic regression. So it's still regression also. So just some differences. There are a lot of similarities. So now, predictors. So this one will be this one. I think the way we put it like that is okay. So I leave it like the way Dr. Additional said, that you should make that one number 1, the general as reference. So the mass score. So if you come here to the model, move program. I prefer it to come, the mass to come after program. Yeah. So let's see the result. How it has affected the race ratio. Can you see? Can you see the program, the vocational, the thing jack up? No, it was 1.2. When you now bring in mathematics score, it jack up. So when we remove the effect of mathematics score, it jack up. Then the other one went down. The academic went down. Are we together? So that showed that those people that are in academic, you see that they were likely, is giving the impression that they were more likely to get award. What was actually behind it was maybe the score, their mathematics score. They're good at mathematics. No, sometimes most of our award they give is tied to maybe some science. Sometimes the people in art they complain that sometimes when people they are encouraged sciences, they say the best in mathematics, the best in all these science-oriented courses. So the person that is good at science-oriented courses may likely get award. Not necessarily that it's better than some people that are not getting award, but because the award is tilted to one the side. So the impression, I see the people in academics, they were getting award more was because maybe those people in academic mathematics, of course, will be more relevant than the vocation, than all those other things, than the general, and that is why. So when you now bring the effect of you remove the effect of mathematics from it now, you now see the thing jack down. Why this one now jack up? Is there any question concerning that? Nobody's answering.
So I'm
Any
just
question?
trying to understand it.
That's why when people are silent also, that's what.
No, I was just trying to process what you were saying, because you were saying that when you remove the effect of math, so that means by entering into this.
But this is not new now. You have done multiple regression, linear.
I understood those ones.
Yes, it's the same thing. It is multiple Poisson regression.
Okay.
Yes, now you are bringing more than one variable. So it's just like when all ratios change, when you bring other adjusted. This one is an adjusted rate ratio now. It's adjusted. Yes, okay. It's now adjusted. That's what I'm saying. Before, this one for program vocation, it was 1.2 or 120%. But now it's become 1.4.
Okay.
Yeah, it become 1.4. Yes, because the issue is that why it was 1.2 before is that most of them, they were not good at mathematics. The people that are doing vocation, they didn't even need mathematics to learn the vocation. So when it was that one, confounder can overestimate or underestimate. So it can work in both. It can work in both ways. Yes. So that was why they was giving impression as if those ones they were not better. When you remove the effect of mathematics from it, you see that some of those vocation, the vocation also, you can see that they were more likely to receive award more than what you were seeing. But whereas the academics, because what overinflated their own is the mathematics, because in the academic, most of them is mathematics. So when you remove the effect of mathematics knowledge, you now see that their rate of that is apart from mathematics now, on the lighter remove mathematics. So their rate of award is not as high as what you were seeing before.
Oh, okay. Thank you so much.
Don't like the adjusted odd ratio. This adjusted, adjusted rate ratio. So any other one? So I don't know if I have another example, but the example is not quite different from all these other ones. I have another. If you look at it, there's another one which I sent. What's the name of that one? Another file. So I don't know if you can run that one also. But virtually it's the same thing. So if you have issue, let me know in understanding, because if you ask me now, okay, how do you bring out the result? Very simple. Just like the way you bring out the result for logistic regression, it's the same thing. So you can decide to bring out the word statistic, the with significant, and the exponential B. There is no odd ratio, it's rate ratio. Or just a rate. You just say rate ratio. The rate ratio, you will not call it odd ratio, it's rate ratio. You call it. And their confidence interval. And the funniest thing is that the confidence interval also, it must not cross 1 for it to be significant. And I even forgot also, you will see that the vocation is not significant here also. If you look at even the vocation we're talking about, it's not significant. I don't know if you can see it.
Yes, sir.
Yeah, the vocation is not significant. So, yes, it's not. So it's actually the academics, this thing, and the mathematics. The academics and the mathematics that are significant. So that shows that all those factors, they don't, whether the program, what do I call it? The vocational program doesn't influence somebody's award, the vocation and the general. But whether you're good at mathematics, yes, academics, if you're in the academy, you're more likely to get award. And actually, to be sincere with you, that's just it. If they give the award to any other people, people will be lazy now. Nobody, because most of the people that try to put their head into hard thing is that what they are looking for. They just want to have that self-satisfaction and work harder so that they can get it better. If you now say that award is for everybody, no victor, no vanquish, well, there's no need to work hard if anybody just gets anything. So, so that's what is telling us here, that they are worried for people that are going to things that require their brain. Not the people that just, there are some professions, you just continue doing it. Even if you are a dummy, you continue doing it, you become perfect. There are some things that you need to think before you can do. Okay. I don't know if there's any. So if you want to do the table now, all you need to do, just like the logistic regression, you may decide to talk about the beta. Some people beta and the word statistics and put it there. You remember the word statistic, the origin of the word statistic is beta over the standard error square, give you what. But if it is this thing, if it is scatter you are using now, it doesn't give you what, it gives you Z. And that one is beta over the standard error, that's all. Over the standard error. So it's still the same thing. As we said before, that chi-square is actually from Z. So for starter, beta over standard error give you the Z. It follows normal distribution. But if you square it, you go further, you follow chi-square. That is the word statistics. So like SPSS present word statistic, something like starter, PINFO, they present Z statistics, Z score there. So any question? Should we go on to run the other one to see the way it look? Or are you exhausted? Please, I want response, please.
I think you should just try it.
Okay. Yes, there's another data this thing there. I think what's the name?
Need the cancer drugs.
Yes, maybe. Is it cancer? Let me see. put it here also.
PF.
I didn't solve it with hand because the logic of solving the two with hand is to solve the one that the exposure is contingency table, and the one you are using proportion, and the one that you are using mean. Can you see now? Just to explanation, that's why I solve it with hand. Psychological and social score may, that's the PAF. Yes, PAF. Psychological and social score may contribute to the occurrence of paroxysmal atrial fibrillation, PF. In a 1 month parallel group study, 316 patients were treated with either verapamil or metoprolol. It's metoprolol. Meto, not metro. Metoprolol. In addition to the treatment modality, the psychological and social score were included as predictors of the outcome variable, the number of episodes of paroxysmal atrial fibrillation. If you look at it also, is another one because you are talking on number of which is known either you have it or not. So, and the other variables are no, there are 3 variables here also. 3 variables. There is treatment, then there is social and psychological score. Of course, you know, just like the way mathematics, you cannot show it on the table. You cannot show that one because those ones are continuous variables. I cannot show it on the table here. So this is a summary of this one. Let somebody share and let's look at, play around with it also. Let somebody share. KAF.
Okay, let me share.
Okay, sir.
I'm trying to share.
Yes, it's coming. Yes. So you can see now we have the number of PAF episode. We have psychological score, social score, treatment modality, which is this. So if you go to the variable list, variable view, we see the way we coded. Yes, and let's see the variable view to see the way we coded. Which one is? Yes, verapamil and metoprolol. Okay, we can let's cross tab the, look at the mean, cross tab the mean, go to analyze the mean episode, go to analyze mean, the number of PAF independent, then treatment modality will be independent so that we can see treatment modality to see how we do our direction of our coding. You have to unshare and share the result. Stop sharing this one and share the result.
Yes.
You have to stop sharing this one, or else you will not see it.
Yes.
If you are,
I'm
you will not see
clicking
it.
on it.
You will not see it. You have to stop sharing now. Share again. You now see the round.
Can you see this? Okay.
It's coming. It's trying to come.
Mm-hmm.
Yes. We can see that the Verapamil has higher mean, right? Yes, than Metropolol.
6.7.
Yes. So, and for the total, the average total is 5.81. So we can. So let's go to. Okay, which one did we code? What was the coding? Verapamil has the highest. You can go back and check. Or I can check here.
Mm-hmm.
You wait, just wait. Let me check.
Oh, okay.
And don't worry, don't go out. Yeah, I will check from my. That should have to go on. Poisson. Okay, Verapamil is 0. Yeah, and Metropolol is 1. Okay, just go to analyze. Analyze. Go to analyze.
Okay.
Yes. So click on. Okay, you have not clicked on either. You have not clicked on. You either click on Poisson Linear or you come and click on custom. Just choose one.
Sorry.
You have to under type of model.
Mm-hmm.
You have removed that thing and we can't see it again. Go to analyze.
Okay. Uh-huh. Okay.
So you either count, look at under count, Poisson Linear. Click on, you have clicked.
Yes. I've clicked on that one.
Yeah, response.
Okay.
Response is a number of PAF. Then predictors. Show the click on the treatment.
Okay.
Option. Just for you to see. Yes. Click on that option.
Mm-hmm.
You leave it as ascending. You know the one that has the highest, the Verapamil is coded 0 has the highest something. So when you say ascending, if you now use the other one that is coded 1 as reference. Yes, I mean, and that is why some people do it like that. When they have the something, they now make the reference to be the one that have the highest number. You get it encoding because you know that by default it put that. But if you have done in the other way, that the Verapamil that has the highest something is the one you coded 1, you have to come and click and set it because you want to make the other one a reference. Yes, I mean, it's okay like this. So you have to remember. Otherwise, continue. So model, move it, treatment, then estimation. Okay, that one says we don't even go to statistics. You can leave it as model based estimation. Go to statistics. include exponential parameter estimate. That's all. Okay.
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 Okay. Sorry, I clicked. Okay, that's already.
So you scroll down. Yes, you will see. You will see that yes, you will see the treatment modality, which is verapamil. Look at it now. The rate ratio is 1.373. That's 137%. So let's run everything
37.
together. 1.37%, 1.37,
Oh.
and it's significant.
Hmm.
So we can go and hide. Let's go and hide it, and let's add the social. We can run the social also separately one, but let's just go and run them.
Where is the?
Okay. Yes. So we're going to move them to covariate. No, they are quantitative. You move them down. But if normally, normally we want to explore each of them one by one first as a different variable.
Okay.
Or should we first do that one as different? Just like
I think we should.
Okay, if that's the case, just put one, maybe psychological first, and remove treatment. Want to see if each of them is significant on its own? Yes, move to model. Model. Now move it there. And click OK. You know every other thing is the same. You already click all those ones.
Okay.
Yes.
Okay.
You scroll down. Okay. So what is showing us is psychological score. The higher the psychological score, the lower the rate. Can you see? The lower the rate by like 2%. Is 0.98. Remember I had. Or 1.2%. So that shows that the psychological score, if the psychological score is okay, the rate will reduce. Who is making, Ogona, you are making noise.
Direction. 0.99. It's like 0.99.
No, that one is intercept. We are talking of that's for the intercept. But we're talking of the psychological score. It's 0.98, 0.99. So and that is reduction because it's not up to 100% now, right? What is telling, we have already said that once it's less than 1, if you look at the beta here, it's minus. It's telling you that the psychological score increases, the rate of paroxysmal tachycardia fibrillation, atrial fibrillation will reduce. So the psychological
score, inverse proportion.
Yes, trying to improve it. Yes, I'm trying to improve the situation. That's what he's saying. Okay, and it's significant. Let's go and do it with social.
Social score.
Separately. So remove psychological and put social. Model.
Back to.
So are other people with us?
Yeah, so it's negative.
And but you will see, maybe the treatment is confounding for the type of treatment. You see, the other one also is showing the same thing. So let's run it together now. It's showing the same thing. Let's run it together. That treatment, the type of treatment, it may be treated to one side. You examine now. Maybe the one that are receiving the verapamine, verapamine are the people that have high psychological symptoms.
Put all of them together.
So actually, that's how it's supposed to be anyway. The social score and the psychological score should reduce fibrillation now. They're all the same. So that one will go to factor. Yes. Model. So move. You know what you do? Remove that psychological score. Remove it first, so that we can arrange it serially. Remove the one inside the model first. Remove yes.
Okay.
Social.
Yes, social. And now select all of them and move them.
Okay.
No, you cannot select anyway. Move that one to. Oh yes, both of them, because you are a model. Yes. Click OK.
The three of them.
Yes. So you see, yeah, it's still the same. Yeah, I think it's the same. Even is I don't think there's much change. Even together.
Not much.
Yeah. Even with the only thing is that even the treatment, that effect of treatment has increased. You know, it was 137, 1.37. It has increased to 1.49.
Now 1.49.
So, but let's see what is the significant. If you now look at it, the psychological score is barely not significant again now. The psychological score. Can you see now? But 0.05 is, you can still consider it to be, yes. So if you want to do the table now, just like the way you do the logistic regression table, and decide to show your p-value, risk ratio, and the confidence interval. Then if you want to show other things, you may show the beta together with the post statistics. Because actually, it doesn't make sense even showing p-value without word statistics, because the p-value belongs to the word statistics. And the word statistics is derived from the beta and the standard error from the beta. The exponential, even though the exponential also is derived from the beta, there is different thing because it's a confidence interval, while the other one is hypothesis testing. Though, of course, if it's going to be significant with the p-value, it will be significant with the confidence interval. So I think general question. Any question? Some people are no more talking. I don't know. Maybe they are outside.
Please, Please, could you explain again?
Yes.
Can you hear me?
Yes, sir.
Can you hear me?
Yes, sir.
Could you explain again the influence of this negative B on the interpretation? You explained it before. I didn't get it.
Yes, very simple. If you remember, even in logistic regression, whenever the beta is negative, the corresponding odd ratio, because it's the same thing, exponential will be less than 1. It means that that factor will make the attribute, the outcome to be less likely to happen. I don't know if you understand me now. Whenever beta is negative, exponential will be less than 1. When the beta is 0, the exponential will be 1. When the beta is greater than, is positive, that is, if it is negative, it means that it's less than 0. If it is positive, it means that it's greater than 0. The exponential will be greater than 1. It means that the factor make the outcome to be more likely. That's it. So, and the logic, the reason behind it is very simple. Since it's the anti-logarithm we are calculating to give the exponential is anti-logarithm. Anti-logarithm of 1 is 0. So anti-logarithm of 0 is 1. So when the log, the beta, it's a log now. That beta is in the log form. So when beta is less than 0, that shows that it's a logarithm of something that is less than 1. So when you do the anti-log, it will be less than 1. If the beta is 0, that shows that it's a logarithm of 1. And you know that when we are talking of this odd ratio and all the interpretation of this ratio, 1 means that there's no improvement, nothing. It does not reduce, it does not increase. That's what it means. Like in this Poisson regression now, where we're talking of rate of event, number of event. 1 means it remained the same. It's 100% the way it was before. It did not reduce, it did not increase. So the factor has not added anything to it. That's what 1 means. And that is, by that time, the beta will be 0. The anti-log of which exponential will be 1. But when the beta is less than 0, that means that the anti-log, that will be less than 1. It means that the attribute, in fact, the more the attribute, the less the outcome. The more the exposure, the less the outcome. That's what it says. But when the beta is greater, is positive, it means that it's greater than 0. So the anti-logarithm, which is the exponential, will be greater than 1. It will now tell you that, oh, the more the exposure, the more the outcome. I don't know if it is easier to conceptualize now.
Yeah, very clear now.
Yeah. Any other one? Okay, I think we'll stop here.
We're fine.
Okay.
Okay.
That's good. You can stop sharing. Let's try to review our this thing. Since today is the last day. So if there's no more question, let me just stop the something that